Hello again, organic dorks. Make sure everything's connected here. Yeah, man. Hopefully you can hear me. We're going to be talking a little bit about a concept known as formal charge, which is more of a bookkeeping method for us talking about reactions eventually. There's all kinds of really important uses for this, and the way that I learned it, which wasn't very effective, was through this equation that I never really quite understood. So I'm going to show you a couple of examples and kind of simplify some things for you, hopefully. So in one of our last videos, we saw that carbon likes to bond 4 times. That's the most important thing to know. Nitrogen likes to bond 3 times. Oxygen likes to bond 2 times. Hydrogen and all the halogens like to bond 1 time. Okay? So you might have been asking, well, what the heck is, what happens if, I don't have a nitrogen bonding 3 times? Well, that's kind of where formal charge comes in. So let's say that we go back to that original compound we were talking about in one of the first lectures, which is a nitrile that looked kind of like this. One of the things that we're also going to see as we go through these videos is that chemists use different ways of representing organic compounds. Sometimes I won't show all the detail for different parts that aren't important. In fact, when we get really lazy in a little while and we start talking about large organic compounds, you'll notice that all I do is lines, and the only real elements that I label are oxygens and nitrogens, things other than carbons and hydrogens. But anyway, we'll get there. So we know from that last video that if we see something with 3 bonds only, it kind of looks like it's not satisfying its octet. Well, it turns out the reason that nitrogen likes to bond a total of 3 times is that it already comes to the game with a total of 5 valence electrons, which means that there are actually 2 electrons that aren't being represented here that look like that, right? And so nitrogen, of course, is going to satisfy the octet rule like everything else. It's just that sometimes you leave those little electrons off. You call them lone pairs. Okay, so that is said to have a 0 formal charge, right? So if you've got a nitrogen as normal with 3 bonds and 2 electrons or 1 lone electron pair, you have a formal charge of 0, right? And usually you don't write anything if it's a formal charge of 0. It turns out each one of these atoms has a formal charge of 0, which I'm going to tell you, and then I'll show you how to calculate eventually. But if you always remember that carbon, 4 bonds, nitrogen, 3 bonds, hydrogen, 1 bond, oxygen, 2 bonds, when you're supposed to show formal charge will be incredibly apparent. So there we've got a nitrogen with a 0 formal charge. Well, what about that thing that I asked about in the warm-up, which technically isn't actually even organic? What about this thing? Right? This guy is called amide. Not to be confused with the functional group amide, which curiously is different, but, hey, chemists just try to make things confusing so that I guess you have to pay our salaries. I don't know. So this guy is called amide, and we know, or you may remember from way back when, that this amide has a minus charge. Well, it turns out that we have to account for that minus charge somewhere, and it turns out that formal charge is going to do that for us. The reason that I know, even if this minus charge wasn't here, the reason that I would know that that had a formal charge of some kind is that it is not a nitrogen bonded to 3 different atoms, right? It's still satisfying its octet. It's still got 8 electrons in that valence shell. But now I have to account for that overall minus charge on that amide. And it turns out the place that that formal charge is kind of told to you by by that rule that we use that nitrogen should bond 3 times. It turns out that nitrogen with only 2 bonds and 2 pairs of electrons is in fact what's called a negative formal charge. So you'll often see either a negative or a negative 1. I don't want to get confuse you guys with the fact that there's kind of 2 negatives there. I'm just saying that this overall thing definitely has a minus charge, and your job is to figure out where the heck is that minus charge in that compound. And it turns out that the formal charge is right there. And how did I calculate that? Well, I didn't really. I just know, I remembered that. But what if you have some sort of structure that you do have to calculate a formal charge on? Turns out it's really, really easy. Don't bother with the craziness in the book, which I think is some sort of equation, which is silly. What you do is you look at the periodic table and find the group that nitrogen's in and say, what is your valence number, right? Well, nitrogen is in that 5th group over, right? And I may do like a picture in a picture thing somewhere around here. But nitrogen is a 5, right? It's a valence shell of 5, or at least it should be. And what you do is you subtract the bonds, okay? So there's a bond, and there's a bond. Now we're going to subtract each individual lone electron. So 1, 2, 3, 4. You'll notice I've got 5 minus 2 minus another 4 for a total of minus 1, right? That's how I knew that that thing had a minus 1 formal charge. It's not hard to do, right? In your book or in many books, it'll have some sort of like 1/2 the bonding electrons minus blah, 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 blah. Just think about it as valence minus bonds minus the number of lone electrons. That's it, and you're done, right? Another thing, like I said, you can memorize 2 bonds on a nitrogen, all things being equal, is always going to have a negative formal charge. Well, what if this amide does what an amide is really good at and actually has a reaction happen, and it pops on like another 2 hydrogens, right? That's what nitrogens in organic chemistry tend to do. They tend to act as bases. In other words, they accept protons onto them, H pluses onto them. So what if we add 2 H pluses to this thing? What's it going to do to its formal charge? Okay, so if I get my body out of there, hopefully you can see this new thing, which is called ammonium. A polyatomic that you probably remember from general chemistry that's pretty popular. Well, it turns out we know that this thing overall, this also you may remember from general chemistry, that this overall thing has a positive charge. Well, that means that we have to find charge in here to overall add up to plus. And the key is to recognize, hey, nitrogen's supposed to be bonded 3 times. I bet you the fact that it's bonded 4 means that there is a positive formal charge in there, and you would be right. Yay. So there's our positive formal charge. How did we figure it out? Wow, let's do that again. We had the 5 for the normal valence of nitrogen minus the bonds, 1, 2, 3, 4, minus the number of lone electrons, there are none. We end up with a +1 overall. And so one of the things that when we start doing mechanisms, you'll recognize that these formal charges are hugely important in trying to predict reactivities and stuff like that. So it's really important at the beginning we make sure that we include them as much as we can. Otherwise, we may not see where reactions happen. But you know, it's pretty straightforward. Next step of this video is I'll show you oxygen, and then we'll probably just stop right there. Okay, so here we have something called propanol. We might as well label it. This thing is 2-propanol, otherwise known as isopropanol. And keep in mind, we'll go through all these naming rules someday. Super boring video, but we'll try to spice it up somehow. So this guy, the OL ending, tells you there's something going on. It turns out that this is a type of functional group known as an alcohol. So that alcohol involves anytime we have an oxygen, which has a hydrogen on one side and some sort of a carbon-containing group. So this particular one doesn't have a formal charge because we'll notice that all the carbons are bonded 4 times, all the oxygens are bonded once, and all the oxygens are bonded twice, yikes, and all the hydrogens are bonded once. So the fact is, nothing has a formal charge, so we're not going to show it. Well, what if this particular alcohol decides to act as an acid and it loses its hydrogen out there on oxygen, which is a type of reaction that alcohols can undergo. Not the greatest acids, but they can do it. Oh, first of all, I should put in the other lone electrons. Once we start talking about formal charge, it's really important that we include those lone pairs of electrons. So what happens if I rip that hydrogen off and those two little electrons right now stick around on oxygen? Well, it turns out what I've done is I've given this overall thing a -1 charge, and that minus charge is right there on that oxygen. So, you know, I know that oxygen bonds twice. Well, it's only bonded once. Something must be true about the formal charge. We'll look at this sucker, and you'll recognize, in fact, that we've got oxygen with its valence of 6 minus the 1 bond minus each individual electron that is alone. I'm so alone. So that's where we get our -1 formal charge. That guy, by the way, is no longer called 2-propanol. This would be now called propanoxide. Propanoxide. That 2-propanoxide is going to be something that's pretty reactive, as is kind of told to us by that formal charge, and we'll see how to handle that eventually. So this guy, what if our original alcohol here acted as an acid instead? Alcohols, much like water, are able to act as both acids and bases with the appropriate pair. And so what if this thing reached out and grabbed a hydrogen and now ended up bonded 3 times? As you might guess, this guy has a plus formal charge, which we could have figured out by saying we've got a valence of 6, we subtract all the bonds, and we subtract those 2 electrons. Woohoo! We get a +1 formal charge. So this formal charge argument is going to be, as I said, important to all kinds of different reactions. In the third day's videos, we're going to be talking about resonance and things like that. Turns out that resonance forms, if you remember those, also involved kind of evaluating the concept of formal charge. So that's kind of where we're headed. All right, bye-bye.